Okay, I'm going to begin this video by saying, excuse my drawings, I tried my hardest. As you can see, the sarcolemma and the voltage gauge channel right here, I put over here. Probably would have been easier for my illustrations and actual going through it if I put it over here, but I didn't. So just so you know, the purple dots are my acetylcholine, the blue dots are my calcium. Over here, this red area, let me zoom in. This red area is going to be my calcium. Okay, so we're going to begin at the neuromuscular junction, and this is where the muscle stimulation really begins. It starts with an action potential traveling down the motor neuron into the axon terminal, which opens this voltage-gated calcium channel that allows calcium to come in the synaptic end bulbs, and it diffuses. This allows acetylcholine to come in. It diffuses into the synaptic cleft, and then it binds to the motor end plate. When it binds to the motor end plate, this allows for the ligand-gated channel down here to open. When the ligand-gated channel opens, this allows for sodium ions to enter into the muscle cell and potassium ions to exit the muscle cell. This causes the membrane potential to depolarize because of the addition of positive charges. Because this depolarized when the sodium ions entered into the muscle cell and the potassium ions exited and created an imbalance of positive charges and whatnot, it opened this voltage-gated channel along the sarcolemma, which it opens, and that basically has the action potential travel along the sarcolemma, down the T-tubule, all the way to the sarcoplasmic reticulum. The T-tubule is important. You don't want it to go outside the cell because it allows for the calcium to be released from the sarcoplasmic reticulum. If you didn't have the calcium release, this whole muscle contraction thing wouldn't really work. Anyways, when the action travels down the T-tubule, it depolarizes the membrane, which in effect opens this voltage-gated calcium channel on the sarcoplasmic reticulum to release calcium ions from the sarcoplasmic reticulum into the sarcoplasm. Calcium binds to troponin, which makes troponin change its shape, and tropomyosin move off its myosin-binding sites, which allow myosin and actin to begin binding. This starts the cross-bridge cycle, basically. So right here, this is where we start. The myosin and actin bind. Then we lose a phosphate right here. This is where ADP is released, and the myosin head pivots and slides the thin myofilament towards the center of the sarcomere. The ADP is released. The ATP is hydrolyzed to ADP and a phosphate, which allows the head to cock. So right here, it's at a 45-degree angle, and it's starting to cock right now, straight up. And right down here, this phase was the power stroke. Oh, my pen got on. What the? Okay, I hope this is the last take. So, that's the power stroke. Oh, no, I'm nervous. So now the head cocks. So when the ATP binds to the myosin head, the bond between the myosin and actin weaken, and the myosin head detaches. I think I said ATP, I meant ADP. When the ADP attaches, it allows the myosin and actin bond to weaken, and the myosin head detaches. This repeats and the sarcomere shortens, and this allows muscles to contract. To stop muscle contraction, the action potential on the neuron needs to stop acetylcholine to being released, or the calcium. Acetylcholine and calcium are both responsible for muscle contraction, so you need to kind of remove both for the muscle to not contract anymore. So what we're going to do is remove acetylcholine from the synapse and stop the release of acetylcholine. So one way to remove the synapse is the enzyme acetylcholine esterase, and that chews up the acetylcholine, and another way is to diffuse the acetylcholine out of the synaptic cleft. ATP is important in this step. ATP is needed to remove sodium and calcium. So ATP removes sodium from the muscle fiber through the sodium-potassium pump. ATP allows for calcium to be pumped back into the sarcoplasmic reticulum from the cytoplasm. Without calcium, actin and myosin can no longer bond, so troponin and tropomyosin shift back into place and block the myosin head and actin. The myofilaments slide apart and the muscle relaxes. We're talking about myasthenia gravis. This is an autoimmune disease that weakens your muscles and makes antibodies for acetylcholine. The antibodies for acetylcholine, basically, as I show in this picture right here, these are the antibodies, and they're going to block the receptor from the acetylcholine from bonding onto the receptor. Right here, these little pink dots are ACHE, which is the enzyme for acetylcholine. Anyways, so the antibody is going to block the acetylcholine from reaching the receptor. This will, in result, make people experience difficulty swallowing, weakness of eye muscles, blurred or double vision, weakness in extremities. It can be difficult to control, but not really that much anymore with all the technology and medicine that we have. We can control it, but we can't treat it. It's like autoimmune disease. There's no treating it. You're born with it. It can flare up. You can have a thymectomy, which is the removal of the thymus gland, and it has been reported that has helped with myasthenia gravis in some people. You can use immunosuppressive drugs and therapy to also help with this too.